even though we already got used to those two cases, we working with them since the definition of the limit, they are called indeterminate forms. The idea of indeterminate forms is when it's, guess what, not determined. But in general, it means it's not obvious. The value of the limit is not obvious. For 0 over 0 or infinity over infinity case, I like mentioning the black hole versus the supernova exploding in the middle of the black hole. Which one is going to win? So, for example, infinity over infinity case, the supernova expands everything, but the black hole shrinks everything to nothing. If black hole is faster, stronger, everything will be infinity. But if the that's supernova, right? If the function at the top, the numerator, explodes faster, everything will be infinity. The one in the denominator explodes faster, everything shrinks to 0. So that's not obvious. Like the same thing, why we just cannot cancel out those things? Because that's not how it works. It's not 0 over 0, infinity over infinity, it's a function that goes to infinity over the function that goes to infinity. And we check the rates. So we're talking about limits all the time. So we have more cases to cover. It's part of chapter 3.7. Let's start with very basic case. Right after 0 over 0, infinity over infinity, we do 0 times infinity. Same idea with explosion and the black hole. I really like this idea. So my students make fun of me that I do talk about explosions way too often. But hear me out. And also, space science is amazing. I really like that. People who hear aerospace engineers, I mean, you're going to be working with NASA. That's fascinating. And it's just the whole idea there is amazing. F is going to 0. It's not 0, 0. It's not a number. F is approaching 0. G is approaching infinity. And now we're multiplying those two. Which one wins? So the black hole is F. Everything shrinks to nothing. G is the explosion, so say supernova, everything spreads very fast. Or the Big Bang theory, there's a Big Bang, everything starts spreading really fast. Which one wins? 0 times everything is 0, infinity times anything is infinity. How about both at the same time? And that's like, how fascinating is that? So, and those ideas have lots of applications. The idea is, everything you see here should be converted to the case we know, 0 over 0, and infinity over infinity, which we know how to solve. People, come on at the back. Do you know how to solve 0 over 0, infinity over infinity case? At the very back, does anyone know? Something about hospital. Anyone know? L'Hopital rule, thank you. So we just learned that this is where you use L'Hopital rule. 0 over 0, infinity, infinity, you do what? What does it mean to use L'Hopital rule? See, I should call names. Maybe I should go to roster and call names. But actually, let me guess. Every class has Max. Max. Do we have Max right now? And every class has Samantha, for sure. Also, recently I noticed Samantha actually becomes not very popular name anymore. Something changed with generations of your parents not choosing the name. So it switched to Hillary, I think. So it's a very popular American names. Alex. Alex is like, I'm not going to raise my hand, freaking no. Muhammad, very popular name. Usually we yes. Oh, come on, people just lying. I'm pretty sure you're lying. Yeah? Kevin. Yeah, we have Kevin. I know Kevin here. Okay, fine. So it's not a complicated question. How do we use L'Hopital rule? Do you remember? Just vaguely. L'Hopital rule, 0 over 0, infinity, infinity. Would you what? Yes?
Derivative of the numerator.
Exactly. You take derivative of the numerator, take derivative of denominator, and hopefully that helps. And you do it again if needed, if it's still 0 over 0, infinity over infinity. So those cases on the right, will you try to convert them into a fraction? Is it possible though? Yes. Can we convert product into fraction? Have you ever thought about that? Sure. Let's try the example of 5 times 8. Surprisingly, that's a simple algebra which people stuck with. Because the higher level of math you learn, the worse it gets to calculated tips at the restaurant. I know, it's just a thing. So 5 times 8, what's the answer for 5 times 8? 40. Can I write it down as 5 over what? 1 over 8. Does it make sense? Because then you divide by a fraction, you multiply by the reciprocal, but reciprocal means 1 over, or flip the fraction. 1 over 8 becomes 8. So it's still 40, do you agree?
Yeah.
Is there any other way I can write it down? 8 over what? 1/5. Do you all agree with that? That's like an interesting puzzle to look at. And the answer is still 40, doesn't matter. If you divide 8 by 1/5, that means you multiply by 5. That's the idea here. Because 1/5 is already division. Dividing by division means multiply. So that means this case, 0 times infinity, which is not a number times the infinity number. It's function goes to 0 times function goes to infinity. Can be written as 0 over, let me change the color again, 1 over infinity, or infinity over 1 over 0. And the answer is still the same. But in this case, let's check. You can use L'Hopital rule. We need to have 0 over 0 case or infinity over infinity case. But 1, let me choose some kind of blue color. Oh. But 1 over infinity is what? 0. Dividing by the biggest numbers you know, you get the smallest number you know. So that is a 0 over 0 case. Boom, use L'Hopital rule. Or, none of this is non-defined, but that's the whole point of L'Hopital rule. So 0 over 0 case, yeah, that's bad. And that's why we cannot just figure out right away what it is. So indeterminate form is when it's not obvious. And that's why we use derivatives or algebra, multiply by the conjugate thing, factoring. But derivatives are the best, basically. So, but it's a good comment. It's not it's undefined. Not as the answer, though. There's some part of it is undefined, and you have to struggle with that. Infinity at the top, but 1 over 0 is infinity. Plus, minus, sometimes D&E, we remember that. Dividing by the smallest number, you know, you get the biggest number, you know, infinity over infinity case. Use L'Hopital's rule. Use L'Hopital's rule. I put LH in the circle. That's just my notation. You don't have to use it. Use L'Hopital rule. Okay, well, let's practice. Oh, in the professional settings, let's put it in a big fat rainbow box, like so. Here's your rainbow box. That will help you to remember what to do. In a professional way, it looks like this. Remember, we're not working with numbers here. We're working with, let me put it in green. Okay. We're working with a limit of f of x times g of x. That's what's happening. X is going to a or infinity or whatever. But when x goes to a, f of x goes to 0 and g of x goes to infinity. That's what we're talking about. 1 over x times x when x is at infinity. That's kind of the example. And there are many examples you will see. We can rewrite it as limit. If you don't know what to do, convert it into the ratio, because L'Hopital rule works with ratios to a fraction. Either I put f of x at the top, then purple color will be 1 over g, or I put g at the top. Choose which one is easier, because then you have to differentiate that. So what is easier to differentiate, arcsine or 1 over arcsine? So maybe the hard function, the weird function, should go to the top. So we don't have to work with the chain rule. 1 over f of x. As x is still going to something. But just at that something, we have a problem. Good. And then we have this idea of 0 times infinity, becomes, let me write down again. 0 times infinity becomes 0 over 0, or infinity over infinity. And you can use L'Hopital's rule. That's the definition. Any questions about that, or like kind of suggestions, hesitations? Suggestions, yeah, I like suggestions, critics. Critics is good too. Better give me critics in class than in my class evaluations. Which coming soon, by the way. But that was recorded, so let's say it was a joke. Let's do your homework examples. For you to know, our evaluations are very important, especially if you're a freshman. At some point, you will receive course evaluation where you evaluate the class and the teacher. So this is very good for students to report something they were afraid to report officially. Maybe someone was discrimination towards you, rude. This is when you were afraid to go to talk to someone, but in evaluation, it is anonymous. So it's very good that they have this idea in America. We don't have anything like this in Ukraine. So we had a very sexist professor and openly saying, Julia, you're a girl, so you cannot get A in math. Like, come on, you're a master student, but it still doesn't make sense that you do math. So let's give you B because you're a girl, and nobody could do anything about it. So I'm glad that here they have this option for you. But also, our salary depends on your evaluations. So if you just have a bad mood, maybe don't make something bad because you got a bad grade. It should be constructive criticism. That's my point. This is the example from your homework and probably exam too. We put something like this. So remember, this chapter goes to the exam on Monday. How do I know this is the case? First of all, it's not a fraction. Boo. If it's a fraction, usually we do L'Hopital rule right away. But here it's a product already. Let's check. X at 0 goes to 0. Log at 0 goes to 0. Yes, no? What happens with the log when x goes to 0? Weird. I don't remember either. If you don't remember, either use numerical sense, which I don't recommend. I hope you remember the graph. The graph of log, we expect you to remember the graph of x and log. X goes like this, line, y equals x. Log reflected. Negative infinity. What is happening from the right of 0 with log? It goes down, 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 like in the song, to minus infinity. That's why there's a little plus mentioned, because actually we cannot approach 0 from both sides. Log is not defined for negative numbers or 0. So this is the case of, fix that, 0 times minus infinity, which is still good. We never actually said it's supposed to be plus infinity. And now you know that you need to convert it into a fraction. So maybe let me write down. Maybe in one of the boxes, I don't care which box, write it down in red, convert. Do you know what convert means? Like rewrite, transform, right? Convert into or just to? Who knows? Fraction. Into or to? Convert to a fraction or into a fraction? Come on, people who know English. No? There's so many local people here who born in America and don't know. Into or to? I'm seriously asking.
Either one is all right.
Oh, either one is fine? Okay, thank you. People who watching this video don't know my face expression, right? It's a simple question. I just don't remember, okay? But actually, that's why I was hesitant, because it feels good both ways. Limit x goes to 0 plus. So you choose which one you want to put at the top and which one at the bottom. Both will work. My recommendation, if something is hard, don't put it in denominator, because then 1 over log will be hard to differentiate. So usually log goes to the top, but actually it doesn't matter. You choose, just make sure you're good with chain rule. Then denominator will be 1 over x. Does it make sense? Is it the same thing? X times log is log over 1 over x. It is the same thing. So this equal sign is legal. That's important to keep stuff legal in general and in math. Let's check what should I do after this. I'm gonna write down limit 0 plus, and then I will have this. Let me check. Log at 0 is still going to minus infinity. Now I did not change. X at 0 still goes to 0. So how come this is helpful? Because 1 over x is my new term now. And that thing, when x goes to 0, goes to infinity. Because dividing by the smallest, again, it's not dividing by 0. It's dividing by 0.0000011 and so on. That is infinity, right? Dividing by the smallest numbers. We have the biggest numbers. Now the notation, you don't have to learn this notation, is infinity or infinity, check mark. We can use L'Hopital rule. You cannot use L'Hopital rule if it's not infinity or 0 and 0. And this notation is good because now I'm going to differentiate. Log gives me 1 over x, while I will keep the color. 1 over x gives me 1 over x squared minus 1 over x squared. So now, let me tell you why I like the notation so much. First of all, do you agree about 1 over x? Yeah?
So if it's infinity over negative infinity or negative infinity over positive infinity, that's okay.
Doesn't matter. Yeah. Good. Thank you for asking. Plus minus infinity, so in this case, we finally don't care because it's a ratio, so whatever. Do you agree about 1 over x derivative? If not, slowly do it by yourself. So my point is, without this notation, which is fine, I will not take points if you don't put notation, you see this in the months, and that's kind of confusing. How can we end up to be with those weird fractions? That's why I clearly remember as a student that this notation saved me brain power of not trying hard to remember what the heck did I do a month ago. So put some kind of notation. Equals, quickly simplify. 1 over x can go to the bottom, minus 1 over x squared can go to the top. Let me color code it again. There are many ways actually you can rewrite this. Choose any way you like. X goes to 0 from the right. Simplify, or answer right now. Minus x when x goes to 0 from the right. As you can see, minus infinity plus infinity end up to give me this negative sign at the end. But because it's 0, the answer is 0. It did not make any difference. That was the question. Does it matter 0? Does it matter we have plus minus infinity over plus minus infinity? It did at the end. It gave me the negative sign, but with 0 it doesn't matter at the end. Can you do it on a test on Monday? That's one very confident yes made everyone feel bad. So you need to make sure you can. This is the classical example for the test. I like putting this on a test. And let's do one more. With the sine and cosine, everyone gets confused with the sine and cosine. I already know it from office hours and in general from previous years. 5 sine x times, well, let's not put parentheses yet. 5 sine x times ln x. And again, x goes to the 0 plus. 0 plus because log cannot approach. For the log, x cannot approach 0 from the left. So again, you look at it, it's like, okay, no fraction. I guess that's the one. That's the case when we have a product. Here's the product of two functions. One function is a sine times 5 or not times 5. You decide. And one is a log. By 5, I mean, I would prefer to kick it out. I don't want to deal with 5 or 1 over 5. So my suggestion, always kick out the constants if you can. And now rewrite it right away. So you'll have 5 limit x approaches 0 from the right, a fraction. So you remember, make a fraction. Convert, transform to a fraction. The hard, Julia says, put the hard stuff at the top. What is harder to differentiate, log or sine? It's kind of up to you, but the derivative of sine is 1 over x. Having that in the denominator is kind of weird. I highly recommend to keep log at the top. Just leave it as it is. Then it will be what at the denominator I should write down? 1 over. That will be hard to get used to, I'm letting you know. 1 over sine x. Does it make sense? Is it the same thing? It's like 8 divided by 1 over 5. It's 8 times 5. Still 40. So let's see if it helped. First of all, why did even we bother? Let's check at the first step. ln at 0 minus infinity, we just checked that graphically or numerically. Plug 0.005 into log, and you'll get huge negative numbers in your calculator. Sine of 0, where does it go? To 0. So now we have infinity over infinity, because sine at 0 still goes to 0, but now it's 1 over 0 case. Continue. So what I heard, the idea is, but didn't you tell me that sine, the limit of sine does not exist? We had it before. Limit of sine does not exist. At infinity, let me put a note somewhere after that. Note, indeed, sine and cosine, limit sine x or cosine x does not exist. Many people remembered it from the first exam, but it's at infinity. Because sine and cosine are waves. They wiggle infinitely many times between -1 and 1. So they cannot decide where to stop at infinity. So it's not like it blows up. It actually does not exist, does not stop deciding which number to stop at infinity. To stop at, I mean, approach to. So, but at 0, it is 0. Sine is 0 is 0, cosine is 0 is 1. So the function is approaching there. Now, we have two ways of doing it. Way 1 is the L'Hopital's rule. We're going to have infinity minus infinity. Infinity over infinity case. I'm going to put a note. Let's do L'Hopital's rule. Here it is. Equals 5 limit. So I'm going to zoom in. This is what we're doing here. X approaches 0 plus. And now, again, 1 over x for log. And then 1 over sine is chain rule. And that's when you decide, are you good with chain rule? You better be, because there's way too much chain rule everywhere. 1 over sine x is sine x parentheses minus 1. Don't put it minus 1 here. Why? That will be inverse sine. Arc sine notation reserved with having minus 1 on top of the n. So put big parentheses and minus 1. That is what we need here. Derivative of that is minus 1 goes down. By going down means multiply. Copy, exactly. To what? -2. Do I stop?
Cosine.
Times derivative of the function inside cosine x. Chain rule one more time. I mean, once again. We have chain rule in this class. Maybe put parentheses. That cosine came out of derivative of sine. Kind of looks horrible, but maybe it's not. Let's rewrite and see if it helped. Equal sine 5 limit a fraction 1 over x. I'm going to write down it at the bottom, dividing by sine x to the -2. I'm gonna put it sine x squared at the top. There's definitely negative sign somewhere in front, and then cosine x at the bottom. X approaches 0. Did it help? I don't know. Let's check. 0 from the right. So if I check right now, I will have sine x at 0 goes to 0, even if it's squared at 0 squared. X goes to 0. Cosine of x goes to 1. So we don't care about cosine. So it's 0 over 0 case now. It was infinity, infinity, and everything flipped to 0 over 0. How interesting is that? From now on, you can choose what to do. Either you use trigonometric functions and rewrite sine over cosine as tangent, and it works. Or you differentiate one more time using L'Hopital's rule and the product rule. So I will go through one case, and then you at home try L'Hopital rule. L'Hopital rule involves this time product rule in a denominator. So what I'm talking about is way 1. Let's do it this way. Way 1 is keep using L'Hopital rule again. And it will work. 2 sine to the 1 times cosine over product rule. It simplifies nicely, gives you the answer. Way 2 is more clever, I would say, more creative. Way 2 is use tricks. When I see sine over cosine, it's kind of itching a little bit to rewrite it as tangent. So 5 limit, let's put minus in front. -5 limit x goes to the 0 from the right. Equals, let's write it down like so. 1 over x. Yeah. Let's write it down like so. 1 over x times, and now I will have sine x times sine x. The goal of that is to have tangent. And then cosine right below some kind of sign. So that's kind of visually now I see, yeah, there's a tangent there. Maybe it helps to have tangent. I don't know. Let's see. So this guy becomes tangent. And then I'm left with sine x over x at 0. Doesn't it look familiar? Familiar. People are very quiet, so maybe it's not. Let me write it down again. Limit. And I will color code it. In orange, I have sine x over x as x approaches 0. And then in pink, I will have tangent tangent. So those are two limits over here. I mean, it's inside of one limit, but it's two limits. Tangent at 0 goes to 0. That makes sense, right? Either you remember the graph, it's a chair going through 0, or because of sine in the denominator, in the numerator. Sine x over x at 0 is 1. That's one of the wonderful limits, which also called special limits. It's a special limit. This guy, we talked about it a lot. Sine x behaves like x around 0, like a line. So that means they have the same rate. So sine x around 0 has the same rate of increase or decrease as x. Same rate over the same rate gives you 1. So the answer is minus 5. No, it's not. Times 1 times 0. That is 0. So tangent still brought everything to 0. That is the idea. And we're gonna move on after that. But what do you think? So that's a trigonometric way of doing it. It's more creative. But if you do just straightforward L'Hopital rule again, it works too. So the answer can be interpreted. So the answer is 0. If we're talking about these explosions and stretchings, the one I like to talk about, look at this. 5, don't care about 5, it's constant. Sine x shrinks to 0 at 0. Log explodes to infinity, just negative. It's huge numbers, but negative at around 0. Who is going to win? Who won around 0? Sine. Sine shrinks to 0 faster than log explodes to infinity. And I told you before, log is a slow function, so usually it loses. Sine x around 0 shrinks to 0. If you draw a sine x as an engineer, if you actually create a device and you drop a ball, the ball will be going down to 0 from the right, a ball. So the question is the ball going to the 0 faster than the log takes this ball down to minus infinity? Apparently the ball goes to 0 faster. Or you can see it as a black hole shrinks to nothing faster than the explosion of a planet. Isn't cool? So the final answer tells you the answer, the relationship between those products, sine and log. And the previous one was x and log. What was the answer for the x and log? X times log gave us what around 0? Go now back to your notes. Where is it? 0. So the idea is the same. Log is slow. So in general, log loses, but don't have it as a rule around 0. Around 0, it's kind of not very clear. But again, x was going to 0 faster than log, which makes sense. Sine goes to 0 faster than log, and sine behaves like x around 0. Is it cool? So in this case, x actually changes with sine really well, around 0. Next case, infinity minus infinity. Finally, I was mentioning to you many times why infinity minus infinity is not 0. You were asking a lot, and this is nice justification is in this chapter. Because it's not infinity minus infinity is a number. Infinity is not a number. Any number you have in your mind, 55 billions, there's always going to be 55 billion 1. So infinity, by definition, is a number always bigger than the one you think about. It's infinitely huge numbers, positive or negative. So it is f that goes to infinity and a g that goes to infinity. And we don't know which one is faster and slower. Idea is the same. Create a fraction. Create a fraction. Somehow.
Is it infinity into infinity or infinity to negative?
Infinity minus infinity.
Oh my.
Yeah. So here's the definition. F minus g as limit of x approaches a. Ideas. Create a fraction. Nothing new here. The thing is, so I put this table again and again every time just to tell you we're working in order, but you don't have to keep copying it. But this is our third case. We did classical one L'Hopital rule on Monday. 0 times infinity we just did right now. Everything goes back to L'Hopital rule right now. So you don't have to copy this. This comes from the first 2 weeks of the class. How to create a fraction. And we already mentioned that before. Do some kind of algebra. Maybe factor out something, create a fraction. Multiply by the conjugate again. It's back. common denominator, and the two things we just recently learned. Laws of logs might help, and trig identities, you already know them from previous classes. Basically transform into a quotient fraction, right? Example, secant minus tangent. When x approaches pi over 2 from the left. Yeah, when you see trigs, I highly recommend to get rid of the secant and tangent and write them down as sine and cosine. Highly recommend. It just really works well for two reasons. First of all, your brain feels happy that you already know how to start the problem on the test or homework. You're like, okay, well, at least I know that. I know what secant is, and I know what tangent is. So let me write it down and see what's going to happen. That's the first very important step to feel confident on a test. The second step, usually exactly that's how it works. Secant, I told you there are many ways to memorize it, but my favorite one is 1 over sine or cosine. If it starts with C, and it will start, if it starts with S, it will start with C. So I know it's going to be cosine. A student told me last year, I really like it. Minus tangent. Tangent, you just have to know, it's sine over cosine. Sine over cosine. Cotangent is the other way around. So know your trigs, basically. Now there's two fractions. One of the steps says create common denominator. It's even already created for you. It's already a common denominator. So let's do that. First of all, maybe there was no problem. I forgot to check. At pi over 2, I don't know what tangent is doing at pi over 2, to be honest. I don't know what secant is doing at pi over 2 because in many countries we don't learn what secant is. But I do know that secant is 1 over cosine x. What does cosine do at pi over 2? Goes to 0. So we have 1 over 0. So this thing for sure goes to infinity. Make sense? I mean, we don't know that it's not like we know it's infinity minus infinity because it's in the chapter infinity minus infinity. You have to actually figure it by yourself. And tangent at pi over 2 is infinity. Do you know how we know that? Because either you remember the graph or any other way. Oh, there's another way. Tangent is like infinitely many chairs. The chairs they have two vertical asymptotes all the time. This one, minus pi over 2, pi over 2, minus pi over 2, pi over 2, with a shift. So I know that at pi over 2, it shoots up to plus infinity. And at minus pi over 2, it shoots down to minus infinity. Infinitely many chairs. While secant is over there on the graph as well. We have at pi over 2, it goes to plus infinity. I don't know the graph of secant, I told you, and it's very okay. Secant, cotangent, those graphs are not very popular. So you should know 3, sine, cosine, and tangent. Everything comes from there. The other way of knowing is tangent is sine over cosine. Cosine at pi over 2 is 0, and sine at pi over 2 is not 0, it's 1. So it becomes 1 over 0, which is infinity. So I know these guys. That's how I see it. But tangent, I do remember the graph, though. Anyways, talking too much. Did anyone actually finish the problem? You create a common denominator. It's cosine x. And you have 1 minus sine x. And you check if it's time to use L'Hopital rule. So pi over 2 minus, no, doesn't mean minus pi over 2. It means from the left. Approaching this vertical asymptote over here from the left. That's what it means. Equals, I don't know, let's check. Cosine at pi over 2 is still, what is cosine at pi over 2? I forgot already. 0. Sine at pi over 2 is 1. 1 minus 1 is 0. It is 0 over 0 case. Yay. I will use L'Hopital rule and hope for the best. L'Hopital rule tells me I will differentiate each side of the fraction separately so that it's not a quotient rule. That's why we like it so much. 1 minus sine gives you cosine. Cosine gives you minus sine. That's amazing because sine at pi over 2 is not 0. That is already not undefined fraction. Sine at pi over 2 is 1. In this case, minus 1. Cosine, did I lose negative sign? I did. This negative sign got lost. Cosine at pi over 2 is 0. So it becomes 0. Isn't it interesting? Infinity minus infinity gave you 0. And you're like, well, I told you so. Yes, in this case, indeed, those were two infinities that matched with their speeds, and the answer was 0. In the next example in my notes, it's going to be infinity, and another example, it will be a number. So do not memorize things. Yes?
Could you repeat how we got 0 at the end?
Yeah, thank you for asking. I was wondering if it was too fast. Sine at pi over 2 is 1. Cosine at pi over 2 is 0. So this is something you don't have on the test as a cheat sheet. We expect you to know all those trigonometric stuff. So minus 0 over minus 1 is 0. Yeah, thank you. Questions, ideas, suggestions? Can you do this on a test on Monday? I like to say that. It's okay to say no, because we just learn it. But the fact is, not to make you feel upset about it when I ask, the fact is, if you know you cannot do it on the test on Monday right now, you're going to sit down and you practice a lot. So reflecting is important to know that you need to practice. Very good. Now, I have more examples in my notes, yes?
So how would we do this infinity minus infinity for ones that aren't trigonometric?
Oh, good question. What if it's not trigonometric? You just use any other kind of ideas. So in my notes, you can check any homework. I saw lots of homework. Log 5 to the x minus log. You use properties. You have to figure out what is log 5 over x using laws of logs and so on. The multiply by conjugate will show up at some point. Those kind of things. The most interesting case comes right after that. Did I have a nice picture? No. This is the weirdest ones. From all the cases, the last 3 guys are the weirdos. Write down 0 to the 0, infinity to the 0, and 1 to the infinity. What is going on here? Because it's intuitively should be simple, and it's not. It's just like you can literally explain it when you go to Thanksgiving and to visit your parents. How odd is that? That 0 to the 0 even exists, and 1 to infinity is not 1? Why? So I feel like that's the most fascinating thing to explain here. Here's the interesting explanation. 0 to any number m, which is not 0, is 0. Because it's 0 times 0 times 0, blah, 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 0, right? M or a, I guess, doesn't matter. To the 0, if m is not 0, is 1, right? Because everything to the 0 is 1. So what happens when they have this case at the same time? Well, depends which speed wins. If you have 0 to the 0, that is not a number to a number. That is the function f raised to the function g. The one inside shrinks to 0, and the one at the exponent shrinks to 0. If the function inside shrinks to 0 faster, it becomes case number 1, everything shrinks to 0. If the function, the exponent shrinks to 0 faster than the one inside, then everything becomes case 2 and everything shrinks to 1. So it depends on the speed. It's a competition. And we're playing with infinities like it's nothing. Nothing. And then let me show you the other cases to impress you right away. Same with infinity. Infinity times a number. It's just infinity times infinity times infinity. Guess what? It's still infinity. But we already discussed that number to 0 is 1. So what happens with infinity to 0? The same thing. If the function shrinks to infinity faster, then everything explodes, not shrinks, right? Explodes to infinity. Then everything explodes to infinity. But if the function at the exponent shrinks to 0 faster, like a black hole, everything shrinks to 1. Because now those huge numbers, it's like billions, are being raised to something that is very, 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 very small. Faster, whatever is inside exploding slower than whatever is keep shrinking it. So the answer will be 1. That's how cool it is. And the last one is the weird one. That's the one that has like a weird intuition behind it. There should be no problem. 1 to the infinity is 1 times 1 times 1 times 1. Why it is not 1? That's just weird. So, because it's a function raised to a function. The function inside does not shrink or doesn't grow, right? It approaches 1. while the function of the exponent explodes to infinity. Still doesn't really answer the question, so why it's not 1? Who can try to guess? Just a second, maybe, no, just a second. Anyone new? Who can try to guess? Yeah, they're kind of the same people. Anyone new? Kevin? Wait. Jacob. There's always Jacob in class. Always. I'm pretty sure we have 3 Jacobs. Okay, yes, I know you wanted to say. You were first one.
Is it because we're using limits, so it wouldn't be exactly 1? It's either a little bit more than 1.
A little bit more is like what?
Like 0.0000000 to the infinity 1.
Like this?
Yeah.
Okay, so
would go to infinity because it's at infinity. It's more than 1. It's going really slowly, but it is increasing forever.
Increasing forever. So 1,0,0,0,1 times 1,0,0,0,1 it's slowly increasing forever. Or what's the other one?
If it's less than 1, of like 0.999999999.
Oh, even smaller. Oh, actually, you're right. Your guess is better. 99999. Then what?
Then it decreases a tiny amount every single time, but decreasing even a little bit for infinity is negative infinity.
Decreasing a little bit. Decreasing, so negative infinity is still increasing. It's just a negative number. Yeah. So the last answer is wrong. Change it. Decreasing forever to
a 0.
0. So that's interesting. Minus infinity is still huge. It's just negative. Decreasing, like you said, to 0. Very good. Does it make sense? Last quiz, ask you a weird question about a. A to the x. A matters. If a is bigger than 1 and a is smaller than 1, the whole answer is different. When it's bigger than 1, a to the infinity is growing forever to infinity. When a is smaller than 1, then it shrinks to 0. Isn't it cool? So we also have to figure out those speeds. Is the function, in this case, it's not really competition anymore. Guess what? This infinity gonna win. Whatever you're approaching 1, doesn't matter. Infinity is infinity. It's too strong. What matters is how do we approach 1? From the left, or from the right? Or in this case, are we approaching 1 and always smaller than 1? Then everything shrinks to nothing because 0.9 times 0.9 times 0.9 goes to 0. Or we're approaching 1 from the right. 1.1 times 1.1 times 1.1 times 1.1 actually is increasing. Isn't it cool? And that's why 1 to the infinity is not 1. It actually can be 0. How interesting is that? Questions about this? Notes? Do you want to add your comments? You want to add to your own comments?
Oh, no. About into versus in, I think I slightly misled you. They're not exactly, both of them would be right in that situation, but converting into means you're changing the form, and converting
to then approaching.
Converting to is you're changing the usage. I'm changing to iPhone because I'm going to start using iPhone. I'm changing into an iPhone because I'm changing myself into an iPhone.
That was a question not related to the problem though. Thank you. Just a second. We're going to do more examples on Friday, quiz on Friday, homework is due Saturday. So you have time. Let's do office hours right now. We have office hours in Wexler building, group studies, tutoring. Use anything you need to prepare for the exam on Monday. So converting into. So it's kind of into its transformation, I guess. Interesting. Very smart.